Hello everyone. Welcome to the first colloquium of the semester. So we're starting today with Professor Giorgio Gratta. He's the first one to speak in this semester for us. So let me present Professor Gratta. So first of all, it's a huge pleasure, Giorgio. Thank you very much for accepting this invitation. It's really great to have you here. So it's an honor to have Giorgio. He's currently a professor at Stanford University, and he leads an experimental physics group, which in the past 15 years has been central to neutrino physics. His most recent interests are in the search for a neutrinoless double beta decay, which would imply that neutrinos are Majorana particles. But Professor Gratta is also involved in fundamental physics experiments and tests of fundamental physics, various tests of fundamental physics. These range from testing the inverse square law of gravity over astronomical sizes to micrometer scales, let's say, and also single photon detection with molecular magnets. So there's really a lot of interesting stuff. And today he will talk to us about his recent developments in fundamental physics experiments using optically levitated microspheres. So thank you very much once again, Giorgio, and please, when you are ready, you can.
Okay. Oh, thanks very much for the very nice introduction. I guess I definitely have to say that I'm very sorry I cannot be there in person, particularly in this case. You know, everybody likes to go to Rio, but you know, well, hopefully we'll make do with Zoom. Okay, so today, as Thiago mentioned, I'm going to talk about, in some sense, my hobby. That is my second activity in my group. That is search for new interactions at you know, new long-range interaction at microscopic scale. And this is done with levitated microspheres. And so we had to learn a number of techniques that are really more like AMO, atomic physics, than our traditional particle and nuclear physics. Okay, make sure I can turn slides. Okay. All right. So I'm going to actually give a little bit of introduction first about measuring gravity at short distance, which is kind of degenerate as a problem with searching for new interactions at those scales. I will then discuss the physics of optically levitated microspheres, and then give you some non-gravity results, or you know, some results which are kind of auxiliary, and then the first results for searching for new interactions in the 10 micron scale sort of regime. The idea is really to be a little bit more broader, you know, broader than just the new interaction search, but show you that this is kind of a promising technique in general. And in fact, since we started this maybe 6 or 7 years ago, there's lots of other groups doing similar things, or at least handling levitated microspheres for various reasons. I guess most people are dealing with smaller microspheres than in our case, but it's kind of very similar in that sense. Okay, so let's start with gravity. So gravity is clearly the most obvious of the fundamental interactions in nature, but as other idiosyncrasies, is also the weakest by far, and somehow related to this is the least well known of the interactions in nature. I'm showing here. Actually, if you just wait a second, I think I can actually turn on the laser pointer, or the equivalent to the laser pointer. There you go. Okay. Yes. Oh, we went away. Okay. Well, can you see my cursor?
Move again. Yeah, I can see. Yes.
Okay. There's going to be some delay, probably some lag, but anyway. Okay. So and so here you can see listed together the 4 fundamental interactions. Order by strength, and also shown here is the effective range. So as well known, gravity and E and M have infinite range, whereas the effective range of the other interactions is very short. There's lots of those idiosyncrasies of gravity can be understood by just staring at this table, in particular the fact that it's so much weaker. There's one more thing that this table doesn't tell us, and that is the gravity, that there's no such thing as anti-gravity. So gravity comes only in one sign. That means that gravity cannot be shielded. And that's really important, because that means that, that you can have very large objects like planets who feel gravity, but they don't feel the much weaker interactions, in particular E&M, because they're all neutral. And in fact, the solar system is a very good conductor. One doesn't think of it this way, but it's a really good conductor. So as soon as you start having a little bit of an imbalance of charge, so on a planet or something, the charge sort of travels. There are electrons that go around that essentially neutralize all the charge. So that's an important thing. Okay, so gravity, of course, as being the most evident of those interactions because it's not shielded, was explored a long time ago. In particular, the first measurements were done by Cavendish, actually with an apparatus that was a torsion balance that is still used today, that was somewhat invented by this guy, John Mitchell, who doesn't get much credit for it. But so this is like more than 200 years ago. And in fact, measurements of big G, the gravitational constant, there's many of them have been done in recent times. They're shown here in the plot to the right. The two most recent ones are done by Chinese group. Current measurements, I have uncertainties of the order of 10 ppm, which is really quite remarkable. But you can also see that there's lots of dispersion, and there is the uneasy feeling that there are some systematics that are not well understood. In fact, the two blue points are from the same group, and they don't agree among themselves, or at least there are a number of sigmas away between the two of them. And this is a 10 ppm level, where if you think about it, the QED coupling constant, alpha is known to quite a bit better than ppb. And even the weak coupling constant, G Fermi, is known to half ppm. So you can see that gravity, even from this point of view, is not very well known. Having said this, measuring G, is this really horrendously difficult problem. At least one wants to do it accurately. But since we don't have, theory doesn't predict G, there is really not, this doesn't seem like it's a way to actually make discoveries in some sense. And on the other hand, measuring the inverse square law of gravity is actually something where you can, there are predictions of various theories, and so one can actually try to test them and hopefully find something interesting there. So now gravity, as we just said, is the least understood interaction. Among other things, it's not part of the standard model. So we don't really have a way, we don't have good description of this. And the inverse square law is generally assumed to work all the way down to the Planck scale, which, if you think about it, is kind of crazy, right? I mean, it's measured down to maybe a micron or maybe a small fraction of a micron in a very poor way, by the way, you'll see in a minute. And so that's 10 to the minus 6 meters. And we just essentially say, yeah, sure, it will work down all the way to 10 to the 35 meters, which of course, would be nice to be able to verify some of this. There are many ways of modifying gravities, or many ways new forces would actually manifest themselves on top of gravity. Generally, those are a way which is not complete, but is oftentimes used, is to actually use a Yukawa potential. And so that describes how the usual GM1 M2 over R gets modified by an exponential term that has a strength that is alpha, that is how large this new effect is. And then the scale lambda is essentially the cutoff, is the length scale at which this new anomaly is sort of, is actually emerging. Okay, so now that I have, so the two free parameters here are lambda and alpha, and those are shown here. So this is our empirical knowledge of the problem, and so on the vertical scale there is alpha, so how strong the anomaly is, or how strong it can be. And on the other scale, on the horizontal scale, there is the range. And I'm giving the range on the top scale in meters. And in the bottom scale, since this is spanning, you see, right, this is spanning like almost 20 orders of magnitude. So it's a gigantic thing. At the bottom, I also have the scale in astronomical units, because when you move far away, that's kind of a more appropriate thing. There's lots of really interesting things. One could spend an entire lecture going over how we know all this. And so, sorry, the black curve or the gray area is what's been excluded by measurements. So by measurements, we know that, say, for instance, at 1 meter, that will be somewhere here. If there is a non-1/r² behavior, is less than, has a strength that is less than partly 10⁻³ roughly speaking. Okay, and now you can see that the most sensitivity is at the distance of the moon, and that's because the moon is a large enough object that doesn't feel any other interaction but gravity. And we've been studying the orbit of the moon with exquisite sensitivity. And so from the orbit, you can actually put some very stringent bounds on new interactions. And so that goes down to, alpha in that case is about 10⁻⁻10. As you move farther away, it becomes less and less easy to do measurements. And you do that from planetary motion or from artificial spacecrafts. But artificial spacecrafts tend to be difficult because they're too small, and so they feel other interactions. For instance, they may vent a little bit of something, of gas or something, and so they recoil against that. So they're not truly inertial. And planetary motion, you're constrained by the, how much patience you have, essentially. So that's why you lose sensitivity there. As you go closer to human scale, you have the regime where measurements have been done with artificial satellites, but you lose sensitivity very quickly, again, because those things are too small. And also when you get closer to the Earth, you start hitting the atmosphere, and so you become less and less inertial. And then there is a region where we really don't know much. That is, if you recall, some of you may be old enough to remember some 30 years ago, there was some sort of renewed interest about fifth force, that was called, and in particular, there are some anomalies at, say, kilometer scale or something, and those have gone away. When you are at those kind of scales, essentially finding new interactions is degenerate with finding oil or finding water or finding iron underground, because essentially the Earth is not an homogeneous body. And so it's very hard to do measurements, and that's why there is this area here where the sensitivity is very poor. Then there is a better region here around a meter or maybe 10 centimeters, which is essentially the scale of the Cavendish experiment. And then you lose sensitivity very quickly when you go to smaller scale. So we've done some work on very large distance scale, but this requires making spacecrafts, and that's kind of a big project. I already have a big project, so I cannot do this. And so today we'll be concentrating with the short distance, where measurements can be done in a lab. So in terms of motivation for this, one can take the point of view that maybe I prefer, and that is to say, well, gravity is such a fundamental thing that, no matter what theoretical prejudice you may have, you need to explore it as well as possible, because we need to know this. But in addition, there are a number of things that point to maybe possible anomalies down there. First of all, gravity doesn't blend with quantum mechanics, and quantum mechanics is the thing that happens at short distance, or that is important at short distance. And then there is the fact that, of course, gravity is much weaker than other interactions. Maybe those two things can be put together, and they point to the same sort of issue. And in particular, when I mentioned the fact that the weakness of gravity may be related to anomalies at short distance of 1/r², I'm thinking, for instance, about issues having to do with theories with extra dimensions, where the extra dimensions beyond our 3 spatial dimensions are essentially compactified, which is a fancy way of saying essentially curled up, like I'm showing here, at some scale A. And so if you have something like this, you see what happens is that, this is your Gauss's theorem. These are the field lines from a point charge. And you see that if you are on the sheet, this thing behaves like 1 over the force becomes like 1 over r. But if you are, if you go far away from this, those lines, the field lines look like parallel to each other. Now, imagine doing this in more than 3 dimensions, where the sheet is the 3-dimensional world, but then on top of this, there is actually more dimensions. And so you see that you can actually have smooth transitions as you go to shorter and shorter distances from some Gauss's theorem, from some particular power in the force that be, 1 over r squared, you actually can transition to other power laws, or as you move to different distances. So and so that's, if you want, you can take that as the main motivation for those kind of studies. Now, of course, as I said at the very beginning, checking whether the inverse square law of gravity holds is kind of degenerate with checking whether there's other forces that emerge at a short distance, and those can, have to be somewhat related to the mass, but they don't have to necessarily couple to the mass directly. For instance, if they couple to the baryon number, well, the baryon number is almost the same thing as the mass. And so you can actually have cases which are not just directly a modification of gravity, but they behave essentially the same way. Okay, that's enough for the introduction, because I'm not a theorist. But now the experimental part, on the other hand, of this is actually very challenging for a couple of reasons from the very, at very high level. The first thing is that the force you're measuring is very small, and this can be shown. It's actually easy to see by looking at the way the force is. There is Newton's constant in front, and then you see that there are essentially the volume of the 2 objects you're studying and their distance. The densities, you can't win too much. I mean, you can make your test masses out of I don't know, gold or tungsten or osmium, I guess, is the highest density element, but that's about 20 grams per cubic centimeter. So you can, and going from water to that, it's a factor of 20, but it's very hard to actually, you cannot get very many orders of magnitude there. And so you're kind of stuck to densities that are essentially terrestrial type of densities. I mean, if you had a neutron star material, that would be much better, but we don't get access to those. Okay, and now so at denominator you have your r squared. So as you go smaller, that r squared makes the force grow. But at numerator, you essentially have the volume to the 6th power. You have the volume squared, which is the radius of test masses to the 6th power. And so you see that essentially the force is going down with the 4th power of the distance, really, because the test masses, of course, to measure things at a certain scale, the test masses have to be no larger than that scale. Otherwise, of course, you're not testing that scale. So you're sort of stuck with measuring those very, very small forces. And at 10 micron distance, we're talking about something of the order of 10 to 21 newtons, which is a very, very small force. Now, in addition to that, so that's actually means that the signal is very small. In addition to that, there is also horrific backgrounds that come from the fact that nothing is really neutral at very short distance. And things can be neutral, but they still have multiple moments, starting from dipole and so on, because things polarize. And since we're in the middle of the pandemic, somebody asked me how masks work. There's all sorts of crazy people claiming that masks don't work, and they say, well, the holes in the masks are larger than the particles they claim to trap. And absolutely, that's true. And the reason is that those little particles polarize themselves and they get stuck to the mask. So the mask has just to have a labyrinth, so you make many collisions. And if you make many collisions, you don't filter mechanically, you just filter electrically. So that's just a very startling example of the fact that very small things tend to stick to each other very much. Okay, so measurements in even recent times have been done primarily with essentially torsion balances, like Cavendish experiment. But those are torsion balances that have been developed to really superb level of technical ability and capability. So this is actually the one from USC Washington that is kind of the leading group doing this kind of stuff, and this is really a work of art. But essentially, so what you do is that you have you don't have the two arms like in the traditional torsion balance, but you have essentially a modulated mass on a disk, and then under it, at a short distance from it, you actually run some sort of drive disk that has also some mass pattern, as you can sort of see here. And so then you look at the coupling of those two things. And in that case, they have like a foil, a metallic foil between the two of them to actually shield electrical interactions. But you see that there's a number of drawbacks of this, and in particular, the fact that the apparatus has a scale of several centimeters. It's like the size of a soda, a Coca-Cola can or something. And so that is very large. It's much larger than the interactions you are, the scale of the interactions you are testing. Smaller, intrinsically smaller is one measurement that has been done, or some measurements have been done. In fact, some of them here at Stanford by a different group, using essentially micro cantilevers on which there is a test mass, and then you look at the motion of the micro cantilever optically as you scan some drive mass that again is patterned under it or next to it. Okay, so this is the state of the art pretty much now, and that achieves this kind of limit. So now what I'm doing, I'm actually taking a detail of the plot of the alpha lambda plot that I showed before, on the left-hand side. And so this thing goes from 1 millimeter down to 1/10 of a micron, where all the action we care about is. And so you see the envelope here comes from a number of measurements done with torsion balances. That's the one is called Washington. Then the cantilever of Aaron Kapitulnik here. And then some of those things, in fact, this one I actually claim is some of those measurements don't have really sensitivity, and they just claim some limit, but they're not. I don't think they're very reliable measurements anyway. But that's more or less the status, the state of the art of this. Incidentally, if you go to even smaller distances, see this thing here goes down by I don't know, 10 to the minus 3 microns or 10 to the minus 4 microns. You really will want to use something intrinsically neutron, and people have been using neutron scattering because the charge radius of a neutron is much smaller than that of an atom. So in that sense, neutrons work really well. Unfortunately, the sensitivity is very poor because you cannot make a bound state of neutrons essentially. But again, this is something, so neutrons in principle are fantastic for this, but in practice, the sensitivity is not there. So, they suppress backgrounds much better, but the sensitivity is not there. There might be some ways around, but that's a different seminar. Okay, so there's lots of, anything that is below and to the left of the yellow region here is to be tested. And so, and there's lots of physics models or theoretical models that are shown here that would put anomalies in those regions. So that's what we want to do. So now what kind of mass sensitivity you need? Just to give you an idea of what's out there, these are some forces that you can actually have. So we weight, a bathroom scale can resolve 1 Newton, and it can weight about 1 kilonewton, which is our weight or the weight of our mass cup, the seal. One of those horrible things that we are told live on our pillows and we breathe all the time, has a mass of 10 to the minus 7 Newton. A bacterium has a mass of 10 to the 14 Newtons. Our friend the virus is more like 10 to the minus 19 Newtons. And then an atom is 10 to the minus 25. In terms of instruments, conventional atomic force microscopes have a sensitivity of the order of 10 to the minus 12 Newtons. And cryogenic AFM goes down to 10 to the minus 16 newtons per square root of hertz. That's the kind of the noise floor of those things, roughly speaking. So we'll see. So if you remember those numbers, I mean, we'll see that our sensitivity is more like 10 to the minus 17, maybe a bit better than that newtons per square root of hertz. But then we'll have to talk about backgrounds. So the idea is to use optically levitated dielectric microspheres. And this was invented, the technique was invented a long time ago in the 70s by Art Ashkin, who got the Nobel Prize for this a few years ago. And so in his setup, there is a microsphere made out of glass or something that is essentially supported by radiation pressure. So there is a laser that comes from the bottom and it propagates upwards and is focused somewhere. And the radiation pressure pushes up the microsphere, but also the fact that there is a focus of the beam confines the microsphere in the in the horizontal plane, and we'll talk about this in a minute. And actually, there's even a photograph here, very poor quality photograph from the Applied Physics Letter article, which I think the microsphere is this, white splotch in the middle, but I'm not even sure. So the idea is the following. So this is the technique is called optical tweezers and was developed much more. So Ashkin did it in air or in vacuum initially, but this is very well known by biologists these days because you can actually grab a microsphere attached to like a polymer molecule and drag this thing around in some sort of fluid suspension or something. So in that sense, it's very well characterized and works really well. Now, we need to do this in vacuum, which is actually quite a bit more tricky because you need to, well, first of all, because you have to load the trap, that is not, somehow you have to pick up the microsphere, which is, once you know how to do it, is trivial, but takes a while to develop. But also you need to essentially, the microsphere becomes isolated from the environment because it's in vacuum. And so you need to actively cool it, otherwise you end up losing it. This thing picks up energy from the laser or something and eventually falls down. So there is actually quite a bit of work that needs to go into somehow providing the friction that the liquid would actually provide, the friction and the thermal contact with room temperature that is usually provided by the liquid. But the idea is that you have the microsphere. If the microsphere tries to go away from the axis of the beam, you can think of it as a little micro lens that will deflect the beam in a certain direction. And if you look at this, stare at this long enough, you'll realize that this is a restoring force. That is you're shooting the photons in a certain direction, and you recoil. The microsphere recoils against that direction, and that tends to push the microsphere back in the middle of the trap. So there is an equilibrium. There is some sort of stable equilibrium, and in addition, we have a feedback that actually keeps the microsphere sort of center of mass steady. And then the idea is that you bring some what we call the attractor, that is some sort of device which is modulated in mass next to it, and then just do the measure what kind of deflection the microsphere is induced to. The trap looks like this. We have actually more than one trap, but they look similar in that respect, in most respects. But this is the one we use for. This is the fancier one, and unlike Ashkin and most, in fact, all of other traps I know, we only use one laser beam because the idea is that we want really to have good access from around the microsphere. So if you remember the picture that I showed before from Ashkin, there is this kind of beam number 2 that is going transversely, and it's used to measure the height of the microsphere. So what we actually do is to reflect the microsphere. Of course, always reflects a little bit of light back, and so we pick up this light and comparing it with the wavefront from the laser that is trapping the microsphere itself. We essentially build an interferometer that measures the distance between the microsphere and this beam splitter, or one of those beams, well, this beam splitter. And so by doing that, so you can count fringes, interference fringes, and measure the height of the microsphere this way. And so you do this with a single laser beam. And we also use interferometry actually in the other 2 degrees of freedom, say in the radial degree of freedom, if you want. And then, so, okay, so this is the input optics, that is what is sort of shown here. This is the simpler output optics shown here. And this is actually where, this is in vacuum, and is where the microsphere is trapped in the middle of this kind of a cube that is gold plated. This has to be as conductive as possible if you want. You want this thing to be equipotential so that the microsphere is sitting in this cavity and it doesn't feel electrostatic forces. But we'll get back in a minute to this. Okay, so I told you that it's tricky to launch microspheres. I think at this point, just in the interest of time, I'll skip how you do this because it's just technicalities. The important thing is that those microspheres are about 5 to 8 micron diameter. And that's actually important. So the size, of course, is important, but how you load them, okay, it's kind of a detail. Now, the first thing you have to do, though, is that when you load the microsphere, you can imagine that this thing, it's a little piece of quartz, and it's very easy to charge this thing up. And so when you load the microsphere, it ends up being had quite a bit of charge on it. And the first thing you have to do is to learn how to discharge it. And it turns out you can do this really well. So this is actually still a historical plot. It's probably the first result we had from the system. and you can see, so this is like a millican experiment, except it's a millican experiment with super sensitivity. And so you can see here, so how do you do this is that, well, you put the those electrodes that I showed here, each of the 6 faces of this cube are actually can be biased independently from each other. They're all floating electrically from each other. And so you can apply, for instance, an AC field between opposite electrodes. And then you look at how the microsphere moves. And if it moves, it means there's a charge. And if it doesn't move, there's no charge. And so that's actually what happens here. And so you see that the signal is quantized. And then it keeps going down this way. And so, you can see that the single electron step has a fantastic signal to noise ratio, essentially. In fact, once you get to 0 charge, you can crank up the electric field that is exciting this. And then you get, so this is a blown up version of the central part of the plot. And you can see that this is 0 to a part, to some very small fraction of an electron charge translated in electron charge. And in fact, this is one of the best sensitivities on what they call millicharged particles. In fact, I have it here. Never mind this plot, it takes forever to explain, so don't worry about it. But the data I showed you before provided this brown outline here in a scale in a plot where the horizontal axis is the fractional charge and the vertical axis is the abundance of the fractional charges. And so the little microsphere, you can see that you can exclude that there are charges which are a fraction of 10 to the minus 4 of an electron sitting on my quartz microsphere, down to some abundance which is shown here. Those numbers don't mean much, I guess, unless you're an expert of this. But that's actually, so this was for a while was state of the art. This paper here is actually more recent from actually my ex-postdoc at Yale and his group, that have improved substantially by an order of magnitude the reach in terms of abundance, not quite as good in terms of charge sensitivity. This is the kind of experiment that was done, I don't know, 20 years ago and more, to actually search for free quarks and fractional charges. And so, and in particular, this was done first of all in Europe in the 80s, using magnetic levitation. This is the Morpurgo's group, I think. And this one was actually Marty Pearl here at SLAC using oil drops. And so you can see that in their case, they looked at much more matter than our small microspheres. So they reached much deeper into abundance. But their sensitivity was only, they were only looking for charge 1/3. And so their sensitivity was like 10% of an electron charge. So we go much deeper in that region, but we're not as good as going down to the to small abundances. All right, so let me continue a little bit and skip some stuff. Okay, so now we actually, now that we can load the trap, cool down the microsphere, and discharge it, we need to actually see how to approach something, how close you can get with something. And so this is just a schematics of what happens inside that cube. Through one of the holes, there is the laser beam coming in from below and then going out above. The microsphere is sitting at the focus, just barely above the focus, where the stable equilibrium is. And then there is a cantilever that comes close to it. And the idea, so it's shown here in a blown up version. And you can see a photograph actually of this, where the distance microsphere to cantilever is about 5 microns. We can actually do quite a bit better than that. This is an old photo. But that's essentially what you have to do. And initially, it's not obvious that even if the microsphere is neutral, that you can actually do that. Eventually, we will get into issues having to do with Casimir forces, but those are quite a bit beyond what we care about now. As I said, polarization effects are important now, and also you have to be very careful that your cantilever here doesn't clip the tail of the trapping beam, because when you reconstruct the position of the beam or the microsphere by looking at its shadow essentially in the beam that emerges from the trap, at least for the time being, this is done by projecting the light onto a quadrant photodetector, and that measures the center of mass, or the center of light essentially. And if the faraway tails of the distribution get perturbed, it can simulate some sort of displacement of the microsphere, even if the microsphere is not moved. So those are some of the things that we are fighting at present. But first of all, okay, so you need to have a reasonably good mode for your trapping light, and this is shown here. So this is a good Gaussian mode, down to some level. At some point, you start having tails, which is never easy to actually fix completely. But and the first measurement, just to demonstrate how close you can go, actually shown here. So here you're just looking the vertical axis of this plot. To the left is the vertical axis, so gravity is pulling down, and this is essentially a 3D mapping of the vector field, the vector force field, and where you can see slices in y, that is the coordinate we don't see, because here we're showing x and z. So y is in the page, and those are rendered by different colors for the arrows. And so this is actually the noise. Remember, I gave you some benchmark for those levels of, for noise. And so the length of this arrow that I'm showing here on top is 10 to the minus 16 newtons. And so the residual noise here is maybe 10% of that. So it's of the order of 10 to the minus 17 newtons. This is done with an integration probably of about an hour or something of this sort. So this is noise. Let's say the microsphere is neutral, and the thing that I'm approaching is also neutral, is grounded, and this is measured. It's the vector field, so it's measured in an array of points, in a three-dimensional array of points that is shown here. That is shown here. So now I can actually take all my vectors here and actually really do like a histogram, and you see that the noise of the order of attonewton or few attonewton. So this is essentially better than cryogenic AFM, or maybe close to cryogenic AFM, not getting quite as close as atomic force microscopy, but being able to scan a substantial volume of space. And in fact, I thought I had, yeah, okay. So what you can do, you can then put a charge on the microsphere, or a few charges on the microsphere, and then bias the cantilever. Now you're mapping the electric field. And this is just, it's kind of relatively trivial, but this is just a way of showing that this really works. And in fact, the arrows are red and red's data, and black is an FEA calculation. I mean, this is just, you know, Coulomb field, so everybody knows how to calculate that. But you can see that the measurement, you know, follows what you expect very closely. Okay, so it's also useful to characterize our microspheres. I think I'm running out of time. To characterize our microspheres, and in particular, you want to measure the mass. And so the way you measure the mass, you know, you could imagine measuring the mass by just simply measuring the laser power, because that is the momentum of your photons, and that counters gravity, so that measures the mass of the microsphere. But this is very hard, because, you know, what you really need to do is to actually measure the overlap integral between your Gaussian field and the microsphere and so on, and you know, this is, it's hard to do this. And so actually one way of doing this, on the other hand, is to put a known charge on the microsphere, you know, maybe 5 electrons, 10 electrons or something, and then decrease the optical field and simultaneously increase the electric field applied. Now we apply an electric field to compensate for the decrease of optical field, and you know, while maintaining the microsphere at the same height, which you can do really well. And you can see that that's what's happening here. So and you cannot get to the point of turning off the optical field completely, because where you use the optical field also to do the vertical feedback. So you need that light all the time, some amount of that light all the time. But you can extrapolate this thing down to an equivalent of no optical power. And you can see actually this little histogram here is like you extrapolate for many, many measurements, and then you look at this, the dispersion, and you see that the dispersion is actually quite small. And you can interpret this as the mass of the microsphere, and that's about 80 picogram for those 4.7 or 4.8 micron diameter microspheres. There's lots of systematic studies here, but you know, that's not very essential. You can also measure with, in this case, electron microscope, the diameter of the microspheres. And again, there's some systematic error analysis done and so on. And by doing that, you also you can actually get the density, which is 1.5 gram per cubic centimeter, quite a bit smaller than fused silica. Those microspheres are actually grown from some sort of suspension with something called the Stover process, which is chemistry, and so I know nothing about. But they are probably somewhat porous, and they seem to be indeed lighter than bulk silica. Incidentally, 3 of those microspheres, you know, there's lots of measurements done here, imaging many microspheres, but in particular, there's also 3 microspheres that were imaged after having been put in the trap and then retrieved on a piece of silicon. So for those 3 microspheres are really well characterized, and they compare really well with the distribution of size of the other microspheres. Okay, you can also spin the microspheres because those things have they are slightly birefringent, and they are polarizable. They're somewhat polarized, and they're also polarizable. And so what you can do is to essentially use, remember, until now we're trying to counter gravity with an electric field in some cases, so we are biasing the electrons above and below. Now instead you can apply a rotating electric field to the 4 electrodes that are sort of on the horizontal plane. And when you do that, you're essentially grabbing the microsphere by its electric dipole moment and spinning it up. And you can then read out the rotation by measuring the cross-polarized light. So in other words, you provide your trapping light is linearly polarized, and then somewhere here you intercept the orthogonal polarization state, and you know, if there was no rotation, you would actually get a constant signal, or maybe even a 0 signal. But as this thing rotates, you get little flashes of light when depending on how your the orientation of the microsphere is. And in fact, you can actually then, of course, reconstruct the angle between the electric field. You know, the electric field is rotating around, And so you can actually measure the angle between the electric field and the electric dipole moment. And so that's what happens here. And in particular, you see that this is the signal coming out of the cross-polarized photodetector. And first of all, there is a big peak. This is frequency here, and there is a big peak at twice the rotation frequency, as you expect, because of course, you know, as you rotate, you go twice. Each turn, you get 2 flashes because you align twice the polarization. You know, you get twice the signal. You know, So that's actually what we call zero frequency here. And then you see that there's, by the way, 2 side bands that are here and here. And those are due to the, and it's blown up here. Those are the libration of the microsphere. So if you think about it, the electric field goes around and the microsphere is sort of following it. I hope you can see me as I'm sort of moving. But if you are in the reference frame of the electric field, the microsphere is pointing to it, but it sort of oscillates back and forth. There is essentially an harmonic oscillator where it's trying to, you know, be aligned with the field, but it kind of oscillates around it. And so those are the side bands here. And as you can, and so you can see, for instance, that if I spin the thing up and then I stop rotating the electric field, the microsphere slowly spins down. And that's because there is a little bit of residual gas. And so there is some friction with the residual gas or some viscosity of the gas. And so from the spin down rate, you can actually measure the vacuum in your system. Also, as you can imagine, this oscillation around the direction of the electric field becomes faster the larger the electric field is, or the larger the dipole, the electric dipole is of the microsphere, or the smaller the moment of inertia of the microsphere is. So if you actually use the measurements I gave you before for the so if you take the mass of the microsphere measured before, you assume the microsphere to be homogeneous, you know what the moment of inertia is. And you measure the electric dipole moment, which is also done above, and so you know what the electric field is. Now you know what the omega is supposed to be. Or the other way around, you measure omega and you extract the electric dipole moment, knowing the moment of inertia and the electric field. And so, you know, this follows exactly what you expect, and so it's kind of really nice. So you can actually measure the electric dipole moment that is shown here, which is about 100 electron micron, which is, you know, quite large actually. Okay, so I told you that you can actually measure the vacuum this way. You can actually do that by seeing the relaxation in the plot before, or you can do it while you're driving it. Imagine you keep driving the electric field going around, and there is a phase lag between the direction of the microsphere and the direction of the electric field, simply because you need a torque to pull it, and so the microsphere is always behind a little bit. As you put more gas in the system, which is actually the horizontal axis, just concentrate on, I don't know, the middle plot here, the one here. As you increase the pressure here, the phase lag increases. You can see here up to the point where you get to half, you know, to 90 degrees. At that point, you lose sync. In other words, at this point, you're not driving anymore because the angle has become too large. And so now you can see that the orientation of the microsphere becomes random. It's sort of stumbling around because you lost lock with your driving electric field. This unlocking field is a measurement of the pressure. Sorry, this unlocking this unlocking phase is a measurement of the pressure, but it's also measurement of the peak, you know, the maximum, or the value of the electric field, or the peak value of the electric field. And so you can see, so that this point is different for different electric field values. So anyway, you can actually use this to actually measure the pressure, and has some advantages compared to conventional vacuum gauges. Of course, it's much more complicated than a commercial vacuum gauge. You can also use it, if you know the pressure, to measure the gas species that you have in the vacuum chamber, which is shown here for many different gases, from helium all the way to xenon and sulfur hexafluoride. So this is essentially doing like an RGA, except you measure just the average mass of the atoms in there. All right, so I should probably, so those things behave like little gyroscopes, but since I'm running out of time, I'm going to actually skip to the first gravity measurement. So the first gravity measurement that we published, in fact, it's going to be on PRD in the next couple of weeks, I believe, is actually, the scheme is shown here. There is an attractor that is modulated. There's a modulated mass where we alternate silicon and gold for the low density, high density kind of things. So this looks like a miniaturized piano keyboard, where the distance between keys is 25 microns. And the thickness of this slab of silicon is 10 microns. This is not shown here, but in reality, this is also all coated with gold to try to make it as equipotential as possible. But it turns out that even the gold has got patch potentials, and it's got patches of potential. And so there are gradients of electric field that move when this thing moves. And since the microsphere has an electric dipole moment, there is some coupling that is actually between the two of them. And so we actually use a shield, which is also microfabricated, and is this, angle shape kind of thing. And so now what you do is that you bring the angle shape kind of thing very close to the microsphere, micron close, and then you bring the attractor behind that, and then you drive the attractor back and forth while the shield is not moving. In the measurement, I'll show you, this was done with about 10 hours of data, about a day of data. The microsphere size was 7.6 micron diameter, so it's a little bit larger than the one I showed you before. The stroke of the attractor going back and forth is 200 microns. And for the time being, okay, so unlike previous measurements of this sort, we actually have sensitivity on all three axes. And there is a signal on all three axes, because if the attractor is exactly centered with the microsphere, there's no signal on the vertical axis. But if you offset it up or down, then you get also a signal up or down. And if you and you also get a signal in the direction perpendicular to the attractor, which is what people usually think about, but also 90 degrees out of phase, there is a signal along the direction of movement of the attractor. So eventually we'll be using all of those, but for the time being, the cleanest signal by far was in Z, and so we just used the Z signal for this first measurement. And the separation is about 15 microns in X and Z, which is shown here. You drive the attractor at a certain frequency, which is 3 Hertz in this case. But of course, you also, but you look at, but the signal tends to be at harmonics of this, because there's many fingers essentially that get scanned in front of the microsphere. So you don't look at the fundamental frequency, but you look at some of the harmonics. Just to give you an idea, the attractor is microfabricated, is shown here. And the shield is also microfabricated and is shown here. Is actually a double side, it's a symmetric thing, and the trapping beam is kind of propagating up in this kind of slot in the middle. And the attractor swings behind the wall of this. In the schematic here, it shows like there is actually the cavity only on one side. In reality, we ended up just by symmetry making something like this. You can actually calibrate this really well by putting, again, one electrical charge on the microsphere, and then biasing the electrodes. Not only that, but you can measure, in fact, also the off-diagonal terms. So you drive in X and you look at the X response. That is the first top left of this matrix, and then you drive in Y and you observe in Y, and Z and observe in Z. But also you can drive in X and observe in Y and in Z. And so all those cross correlations are known because they've been actually sort of tested. So we know all this. Now, why that happens, why the system is not entirely diagonal, you see that the non-diagonal elements are of the order of 10% or maybe 20% or something. And that is, you can imagine easily, for instance, if the electrodes that apply the electric field are not exactly perpendicular to the direction of gravity or to the propagation of the beam, you have crosstalks essentially between one axis and the other, which is presumably what's happening. Okay, that was the movie that I cannot show you, I believe. Yeah, I cannot show you because this is a PDF file. But anyway, this is just a movie of the attractor going back and forth, and the microsphere in that slot that you see there. This is looking from above. We have a couple of microscopes that are calibrated and they look inside that are used to actually do metrology in there and measure the distance and all sorts of things. The microscope I'm showing here is the one that looks from the top, and is the one that has actually all sorts of aberrations because this is looking through the trapping beam path, and the trapping beam path goes through some parabolic mirror that has some aberrations that they're not corrected in the microscope. But anyway, it's good enough for what we're doing for the time being. So this is actually this first gravity run. And this is just essentially a proof of concept for the time being, but to get our sort of feet wet. But you can see now that this is the frequency. The fundamental of excitation is here at 3 Hertz, and this is the force. The noise is shown by the red and black histogram. The difference between red and black is that black is when you don't move the attractor and red is when you move. And you see that when you move the attractor, there are, the red is when you move the attractor. So that's actually the sine signal, if you want. And then the blue, so that's actually what I'm saying. The blue is actually the signature of the signal from a new force. Because at different frequencies, you are supposed to see a different thing. And so the idea is that what you want to do is that you want to actually see whether the fingerprint of the spectral shape that you observe is actually consistent with the new interaction. But on the other hand, you see that the continuum noise, that the noise of the system is almost the same whether or not you're moving the attractor, which is already sort of good news. But there is background, because you can see that there are some lines that appear only when you're shaking, when you are moving the attractor. And in particular, there's a line here, there's a line here, there's a line here. And the rest actually are lines that occur also without moving the attractor. So those are intrinsic of the system. And there's, of course, a line at 3 Hertz. But of course, you don't want to look at this, right? But there is definitely a line at 3 Hertz that appears when you move the attractor. Okay, so we are very conservative. Okay, sorry. Let's see what else. This is just looking at the Z channel, or the Z direction, and you can also look at function of time, what happens to your signal, and in particular here we're showing the 6 frequencies where we expect the most of the signal to be. And so you see that there is a little bit of a drift with time that we need to understand. But generally, we haven't discovered a new interaction because this, because there's essentially, the data doesn't match what you expect. Okay, so for instance, just to give you an idea, right? This frequency here is missing completely. This frequency is missing completely. Those 2 frequencies should be very strong, and they are missing completely. So we're looking at some sort of background of some sort. This is a little bit of looking at systematic effects, but let's not worry about this for the time being. One thing, so you may wonder what this background is. And one thing we've done is to essentially simulate or calculate the force due to the interaction of the electric dipole moment of the microsphere. I told you before we measured that with a contact potential between the shield and the attractor. So this is a bit complicated. The idea is that the shield removes patches, the gradients of electric field on the surface of the attractor. Those are removed by the shield with very good efficiency. We've simulated this, and it's some orders of magnitude reduction. So that should really not be no problem. However, one thing we did not think about is that as you move the attractor, if there is a difference of potential between the attractor and the shield, there is some field leaking out that actually couples to our dipole, some gradient leaking out that couples with our dipole. And that would be what a contact potential. I mean, nominally, those two things are tied to the same potential. They're both grounded, but there are contact potential in the system, or they can be. And so using a totally reasonable contact potential of 50 millivolts and the kind of electric dipole moment we see, we actually get a signal. Okay, now I should have compared it, but that which is very similar to the one we see. So other backgrounds may be stray light and then probably vibrations. And then things like laser pointing noise and Casimir forces are for, say, next year. I mean, for the time being, we're far from that. So we very conservatively put a limit. The limit doesn't use all of the constraints, doesn't use the fact that the signature doesn't really match what it should be. But essentially takes the worst frequencies or some of the frequencies where we have signals and uses that to actually calculate an absolutely worst case scenario limit. And you can see that we're still not competitive with other experiments. But this is just the first time we've done this kind of measurement. So I'm going to skip this and just go to the conclusions. So after 200 years of using mechanical springs to do this kind of measurement, this is the first time when this is done in a way that is completely using only optical sort of springs, essentially. It's taken a while to get to this point, but I think at this point we have a pretty robust system in which we think we'll understand the background much better than what people have done before. Some of the measurements you see here done by others have backgrounds, but they're sort of, they're not treated in a very systematic and I would say robust way. And we think we have actually handles now. In fact, we already now we understand the background much better than a few months ago when we actually put that paper out. So this is actually moving very fast. Along the way, we discovered a number of other tricks. When you spin the microsphere, I told you that you can measure the pressure with it and use it as a gyroscope and so on. But you also, what you do is that your electric dipole moment scans in front of the gradient of electric field at the frequency of rotation of the microsphere. And so you can use that to measure this kind of background field, which is something we're doing now, and that's why I'm saying we're learning lots of things about this. And so hopefully very soon we'll become competitive, even sort of formally on this kind of graphs. And that will hopefully happen sometimes in the fall. We're actually doing a number of upgrades to the trap. And so when we put it all together, we hope we'll be in a better place to actually do new measurements. And with this, I'll show you my collaborators, which are all doing all the work. And there's also young people doing all the work. And they're shown here. In fact, a couple of them are gone already. Akio at this point is at the Japanese Institute of Standards back in Japan. And Alex Ryder is SRI in Boulder, Colorado, doing more useful things. We also, these are our funding agency, but we also have some sort of periodic collaboration or cross-check with our alter egos. That is the group of David Moore, who's my postdoc and is at Yale now. And so we compare notes with them. And in fact, that group also contains Fernando Montero, that I think comes from your institution, right?
Yeah, he does. He's my friend.
Yeah. All right, there you go. So, okay, good. So that's it. Thanks very much for the attention and for inviting me. And I'll take questions if you have some.
Well, thank you very much, Giorgio, for the excellent talk. It's a beautiful experiment. I see Enyo is here, so maybe he has a question, or I don't know if anyone from the audience wants to make questions now. So Gero raised his hands. So please feel free to also Enyo.
Okay, yeah, thank you very much. I also enjoyed very much your talk. I just wonder, so do you have any projections how you can improve the limits on these ADD extra dimensions? Let's say for 1 or 2 extra dimensions, are there any projections that you can make? What you can measure in the future? Can you improve on this Cavendish experiments?
So you see here, right? I mean, our limit currently, sorry, let me go to a better version of this plot. Yeah, our limit now is the red and blue curve. Red and blue are for positive and negative alphas, but anyway, and you can see that we are, we are a couple of orders of magnitude from the region that is interesting. Our projected next run is this purple thing, so that will cut some region down here. And now, what this means in terms of the various models, I would say it's up to theorists to actually tell us, but this will cut down into this new territory that is unexplored. So we hope that this is going to happen in the next, I don't know, maybe year or maybe couple of years.
And maybe a quick other question related to the Casimir force. Did you make some kind of estimate that this will be a relevant background for you in this region of sensitivity?
Yeah, so Casimir force, thank you. Yeah, Casimir force will become, you can see that the present measurement is, 10 micron is the sweet spot for this, 10 micron is where this thing is with the current setup, where we have the best sensitivity, maybe few microns to 10 micron. When you go below a micron, Casimir force becomes really the most important background. But above, in this region of few microns to 10 microns is not, that's not the primary background. Okay. That's done by calculation, right? So
it would actually be nice to measure it. I mean, I think it has been measured already, but I mean,
has been measured by many people. Mostly this is done with AFM, essentially, with atomic force microscope. I mean, eventually we'll get to the point of seeing it, but not yet.
Okay, thank you.
But Giorgio, in AFM, the spheres are much bigger, right? Or is it?
No, well, no. Atomic force microscope, there's these things where they have something that looks like a needle, and it scans a surface. You can see, single atoms or atomic clouds.
I remember that they stick like a sort of microsphere on the cantilever and.
So, yeah. Sorry. We're talking about different things. So the measurement of Aaron Kapitulnik and company done with a cantilever that had a sphere that was somewhat larger than this. I don't remember. I have to go back to the scale. Also, it was not necessarily a sphere. That was a little cube of some material. When I say AFM here, I just mean the generic atomic force microscopy kind of setup that is used usually to actually scan a surface and look at the atomic structure of a surface. And that, of course, doesn't have a sphere, it has a little atomically sharp tip.
Sure. Okay, thanks. So, Enio had a question also?
Yes, I come from a different area, so perhaps my questions are naive, but nevertheless, can you do these experiments with one microsphere, or you may have several microspheres, so they interfere to each other? So this is my first question.
Yeah, so that's actually, it's not a naive question at all. That's a very good question. We all talk about preparing arrays of microspheres, and that certainly that's a possibility for measuring new forces, for searching for new forces. I don't see how that would help, but there is a number of other things that one can do. For instance, my friend at Yale is thinking about trying to search for dark matter by looking at recoil in microspheres. And there, in order to increase the signal, you want to have many, you need lots of mass, and so you can have an array of microspheres. Loading those traps must be really hard, because now, to put microspheres in one trap is already relatively difficult. And now you have to do it in many traps next to each other without kicking off the microsphere from the first, making sure that you don't undo what you've just done by adding more microspheres. So I think there's a number of technical difficulties that we haven't really solved, but also maybe we haven't really done enough work to say whether it's really hard or not. But that's certainly a possibility, an interesting direction.
Okay, the second question is, how do you monitor the angular velocity, what you call driving signal spinning without? So how do you measure that?
Yeah, so that is, sorry, let me just go back to the right slide. The microsphere is slightly birefringent, and so looks like so when you can see here the scheme to the right, there is the trapping beam is linearly polarized into the, on the parallel to the page. And then the microsphere rotates just a little bit. There is a small intensity of polarization that goes in the orthogonal direction because of the microsphere birefringence. And so now you extract the light of the opposite polarization state and you look at it with a photodiode, which is sort of shown here. If this was PowerPoint, this was a movie showing the thing turning, but the movie doesn't run because I'm using PDF, and so you cannot see that movie. But okay, so essentially it uses the birefringence of the microsphere.
Okay, thank you.
Sure.
Thank you, Enyo. So Hiroshi also raised his hand right now.
Yeah. So this is Hiroshi.
Oh, hi there.
Hi. Thank you very much for the very interesting talk. Maybe this is a stupid question, but I'm wondering if this kind of technique or optical tweezer can be used to determine more precisely the gravitational constant, because as you may know, gravitational constant is one of the fundamental constants which has a worse precision, right?
Right.
So
yeah.
I'm just wondering, is it? I don't know if somebody considered.
Yeah.
Or you have some comment.
So on and off we talk about this. I can tell you my opinion, right? I don't know, but there might be I'm missing something. I don't think that's so. When you measure the gravitational constant, big G, it's a very different ball game because you want to have the best possible absolute measurement, and you want to have the largest possible signal, and presumably as little background as possible. And here, the microspheres are good because you can get very close and make a very short distance measurement. But if you measure big G, you want to do it in the place where you can measure it the best, and at the distance where you can measure it the best, in the best possible way. So I think actually I would not do it with microspheres. I would just do it with something like a kilogram mass or something, which is, I think, more or less what the people doing this do. So I personally don't think this is the right way to measure big G, but I may be wrong.
So the more traditional torsion balance will be better.
There is something called I forgot, it's called the what? There is some other apparatus that is used to measure big G. It was actually on the front cover of Physics Today maybe a year ago. And I think that you can imagine that that's probably the better way of doing it. But yeah, so yes, I think that's actually my personal. But I'm not really an expert. Measuring big G is really a metrology issue, and there's people who have essentially made a career doing that. So I really cannot claim to have much authority on that. Let's put it this way.
Yeah. Okay. Thank you very much.
Sure.
So more questions from the audience? Anyone? Please raise your hands if you have a question, so we can. So so João Felipe Chaves has a question. So please, João.
Yeah. First, thanks, Professor, for the presentation. I really liked it. I was wondering here, you've shown in past slides that you approach the cantilever to this microsphere while it's levitating, and you've shown the diffraction pattern of it.
Yeah, I'll go there.
Okay.
This one.
Yeah, that one. I was wondering here, like, you use the diffraction pattern of the microsphere to measure the force which is acting upon it, right? By the attractor. If I understood it correctly.
To a large extent, yes. Yes, ask me the question because I may answer, yeah. So yes, the answer is yes. Essentially, we're looking at the diffraction pattern to measure the position. Depending on your question, I may want to elaborate more on this.
I was wondering here because you also will get a diffraction between the cantilever and the microsphere because they are quite close together and they have the same order of size. I was wondering here if that wouldn't affect the measure in the end.
Yes, good. That's perfect. Yeah. So very good question. In fact, that's one of the backgrounds. Let me go forward a little bit. Sorry, I guess with Zoom is kind of slow in moving slides, but it's actually one of the slides I skipped. Yeah, okay. So first of all, is this thing about stray light. So, but let me go to the, yeah. So now that center, the diffraction pattern is not really seen. You know, what that picture I showed you is done with a microscope, but that microscope is not fast enough to do the measurements because the well, you know, the diffraction pattern is also used to, or the position of the microsphere from the diffraction pattern is also used to feedback and provide the feedback signal that runs the optical tweezer system in general. Now it turns out that so first of all, there should be no change in the diffraction pattern when the attractor moves, because there's a shield in front, and the shield is designed mainly to be an electrostatic shield, but also blocks the, you know, it's something that doesn't move and it shadows the light. Because, sorry, I just a bit painful to go through the slides. Because, yeah, you see the light, you see on the left, right? The trapping light goes into that kind of slot, and the attractor is behind that slot, you know, behind that shield. And so if there is a modification of the light field due to the shield, that doesn't move. There's no motion because the attractor moves behind the shield. So at first order, there is no problem. But then, of course, everything, you know, vibrates a little bit, and there's all sorts of other things. And so we are building, there you go, we're building something which will replace the quadrant photodetector that is a pixelated photodiode. And you can see it here. This is like 10 by 10, so it's 100 pixels. It's like a very, very fast camera, so that now you can reconstruct the image continuously. And so now you can distinguish much better the motion of the center of the microsphere from the kind of halos like the diffraction patterns and other things that happen around. See what I mean?
So it's like you're not using the diffraction pattern anymore to measure the,
well, no,
the
actually,
movement.
in some sense, you're using more information on the diffraction. So you know, I cannot draw here easily, but so imagine that you have a round diffraction pattern, like there's no attractor and no shield. Now you introduce the shield and the attractor, that will become something that looks more like a D shape. Instead of being circularly symmetric, it's got some sort of facet on one side. And if you only use a quadrant photodiode, well, you know, you don't know that there is a facet. You only know that the thing looks a bit different. If you have a pixelated thing, now you can see that this thing is not round anymore, and you can, you know, you can do a fit that essentially separates the roundness or non-roundness from, you know, the fact that it's asymmetric versus whether the center of the diffraction pattern is moved and all this. So having some sort of rudimentary imaging system will help from this respect. So,
okay,
yes. Yeah, and the other thing is, you know, that's, I think one of my slides says we're reducing vibration in the system. That the, as I said, you know, the shield is actually doesn't move when the attractor moves, but that's of course not entirely true. The shield always vibrates a little bit because, you know, the entire system vibrates, and our system was not particularly good. There was lots of vibration in the optics, and so we are actually upgrading some of the optics supports to be much stiffer and much heavier, so that it vibrates much less. So we hope that this will also help reduce this kind of effect.
Thanks a lot, Professor.
Thank you very much. Any more questions? So actually, Giorgio, do we have time for more questions? Because I remember you.
Yeah, that's okay. I have another meeting coming up in half hour, so there's plenty of time.
Okay. So I have a quick question actually. So you mentioned that quantum limited measurements are possible. So I wanted to ask you a little bit more on that, if you could say something about it. And whether do you think, because you know there's Marcus Aspelmeyer in Vienna, of course, is doing all these measurements on quantum levitated objects and so on. And if you think there's a room for some quantum metrology in these fundamental experiments to measure small forces.
Yeah. So now that's, of course, that's a very good point. There are groups, in particular Marcus Aspelmeyer's group, that are, remember at the beginning I said there's a number of groups now using levitated microspheres, but they are generally smaller than ours. If you're doing quantum measurement or quantum limited measurements, so generally you do this with smaller microspheres, and you can actually levitate I don't know, 50 nanometer diameter microspheres, so 100 times smaller than ours. And I think the quantum behavior has been explored much more in that sort of regime than in our regime. Our microspheres are kind of large for that. There's something that I don't have a curve for this, but quantum limited noise that essentially is a shot noise from the granularity of the light, of the trapping light, that will get to probably, not soon. But actually to do quantum measurements, you want smaller microspheres. And for doing the kind of measurements for the new search, for the search for new forces, you really prefer to have larger microspheres. So I think for my group, at least, we are not going to get into the quantum regime for a while because, we have to do, so because our optimization leads us somewhat away to the sweet spot of quantum measurement. So I think those two groups will probably be somewhat complementary for a while, at least. Yes.
I see. Thank you very much. Any more questions from the audience? So I don't see any raised hands. So let's thank Giorgio once again. Thank you very much, Giorgio, for this excellent talk. It was really
and thanks very much for having me. This was, as I say, not as much as a favor, as a pleasure as visiting you in person, but certainly this is actually very nice to have you in general, to be there virtually.
I don't know if it makes any difference, but it's raining now in Rio. So even if you are here.
Oh, I see. Okay. Then it's sunny here. So that's.
But we will have other opportunities for a visit in person, hopefully in the future. So really, thank you. Really,
thank you all again. And yeah, thank you.
Thank you.
Bye-bye.
Bye now.
Thank you. Bye-bye.